Okay, so I will be talking about sequences of measures on compact spaces. So let me introduce you simply to the topic. So we start with, first of all, it's a joint work with Lubomir. So knocking goes also to Lubomir after the talk.
I noticed the two of you in here like 10 hours a day or something. You're working hard.
Yes, we are.
Yeah, he made you work.
Yeah. Okay, so K always be an infinite Hausdorff compact space. We do not assume anything about the space. And if we have the space, then we can assign the space of real-valued continuous functions. Okay. Space of real-valued continuous functions.
They're bounded already, you have to transform.
Yeah, they are bounded. They are continuous on the compact space, so they must have been bounded functions on K. And this is a linear space, and it has also a metric induced by a norm, and this norm is given by simply by the supremum.
Is it a Banach thing?
And this norm makes it a Banach space.
That's why Banach invented Banach spaces from this example.
This was one of the reasons, I guess. It was everything went from functions, and yeah, they started to consider spaces of functions. Okay.
The K can be enormous. It doesn't have to be size continuum or something.
Between to the X.
Yeah, it could be gigantic.
Mm-hmm. Okay, if we have the space of functions, we can also assign another space, namely the space of measures on K. So this is the space of measures, and these measures are nice, which means that they are, first of all, they are Borel measures.
The domain is the Borel.
Yes, the sigma algebra of Borel subsets of K. They are regular.
You're talking about the probability measures?
All measures. So they are finite as well. Finite. So that means that can.
No infinity.
No, they are finite, but signed. They can have negative values.
Irregular meaning?
Regular means that whenever you have a Borel set, then the value of measure can be approximated from below by compact sets, or from above by open sets.
It could be negative.
Yes, every measure in fact can be decomposed into the negative and positive part, and then you can do those tricks. So.
Are you saying that regular and tight are the same on compact Hausdorff spaces?
Yes.
Is that true? I didn't know that.
What's tight?
Tight is approximating from below by compact and regular.
Yes, yes. I think for compact this is the same as tightness.
So compact.
Oh, it's the same. Okay, that's interesting.
Oh, you want sign measures?
I said compact.
Yes.
It's the same as.
You want to subtract measures.
Yes, and I will. Finite signed, and finite, what finite means? Finite means that they have a variation which is finite. And what is a variation? So if we have a measure on K, then its variation is finite, and this variation is just defined as a supremum over the values of the measure on all n-time chains, finite n-time chains in the space. So this is the same as such that Yeah. Here are pairwise disjoint and Borel.
The measure. Is there a theorem that you can split the space into two parts where this
Yes, this Han decomposition, yes.
So is
In fact, yes, in fact, we can put here just one and consider two parts, yes.
So sum is like the maximal, yeah, okay.
Yes, 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 yes. But in a moment, we will go to some a bit different setting. So there will be, it will be much harder to compute it. Okay, they are pairwise disjoint. Yeah, n is finite, but it can be also omega. Okay, so this is the variation, and actually this is the norm on the space, and this norm makes it also a Banach space.
Everything's fun.
So everything is a Banach space, yeah. Everything which is nice is a Banach space. Okay. Yeah. So this is finite. Okay, and finite means that we can get negative values. Okay, so I say that there is the topology given by the norm, but there is also another topology given by this object. Namely, there is a relation between ck and mk that whenever we take this is a linear space, so we have linear functionals on the linear space. And so we can, as it has a topology, we can look only at those functionals which are continuous in this topology. And then, because we have a bunch of functionals which are continuous, we can think on this ck about the topology, which is the smallest one, which makes those all functionals continuous. And in the other direction, let me show you how. So weak star topology. Weak star topology on mk. It's called weak. So this is the topology given by the values of measures on functions. And what is the value of the measure on a function? It is just the integral over the function f on the space k with respect to the measure mu. So this is just k.
So mk is the dual space, is a subset of the dual space, or is the whole dual space?
Actually, this is a dual space, the dual space.
It is the dual space.
Yes, this is the Riesz representation theorem that every functional can be represented actually in this form. So for every linear continuous functional on this space, there is a measure such that this functional looks like that. Okay, so to define the topology, we just define the open sets over the measure. We have to take some functions. So we take a bunch of finite functions and some epsilon positive. Those belong to ck. And this is just all those measures belonging to mk, such that their values on the functions are smaller than epsilon. So this is the base of the topology. But for our purposes, we only need to understand what is convergence in this topology. So we say that the sequence mu_n converges weakly star to a measure, some measure mu, and this means that for every f which is a continuous function, the values of integrals converge to the integral with respect to mu. So mu_n of f converges to mu f. And with this topology, we have a nice situation because, for example, the space K embeds itself into the space Mk. So for every point from the space, we can assign the 1-point measure, dx, delta x, and this belongs to Mk. This is the measure which takes value 1 on every set containing x and 0 on every set which does not contain x. Okay, and this assignment actually is a homeomorphism from K into Mk with this weak star topology. So delta is a homomorphism. It's an embedding. Okay. Okay, if we talk about those deltas, it's nice to understand what is the measure, what is the norm of the measure, which is a linear combination of deltas. So if we have a measure which is just some finite linear combination of deltas and each points are different, then the norm is just the sum of the epsilon, yes. So this is the absolute values, the sum of absolute values of alphas. Okay.
These delta x, i.e. the linear function already defined, is just evaluating the function at x.
Delta x of a function is just value of function on this point.
So this space is rarely or never reflexive? Or
Which one?
the first CK.
CK is never reflexive.
And do you know what the double rule looks like?
It's weird. In some situations, you can compute it. For beta omega, it's hard actually, and it's not well understood what is the space. But when you take, for example, the very simple compact space, which is just a converging sequence, then the measures are just countable combinations of this form, and the dual, so linear functionals on the space of measure, is just the space of all bounded sequences. So this is the space so-called L infinity. And on the other hand, this L infinity is isomorphic to the space of functions over the beta omega. So this is so going further with the it gets much more complicated, yes.
And 2 to the omega is also difficult, I guess.
2 to omega?
2 to the omega.
2 to the omega? This is a Cantor space.
Yes, and then.
And this is a metric space. Then the space is CK is separable. And for all, I think this is well understood, because then for all, if we have a pair of infinite compact, I think. Wait. How is it? Oh yeah, if we have a pair of infinite compact metric space, then CKs are isomorphic. If we have, for example, C of Cantor space, then it's isomorphic to the C of interval. So for metric spaces, it's
space there's only one.
Yeah.
Okay. Should have a name then, right? Okay.
Oh no.
Oh.
Oh no, this is different.
Should be uncountable.
Uncountable, yes.
Uncountable.
So for metric space, we don't have too much choice. Okay. Okay, so why I wanted to talk about these topologies? I wanted to talk because there is a very nice theorem due to Josefson and independently Nissenzweig from, I think, 71 or 2. And it states that if k is infinite, so as we have, then it says that there exists a sequence of measures such that those measures converge weakly star to the measure 0, and each measure has norm 1. So this actually shows that the topologies are different, very different. Of course, weak star topology is weaker than norm topology, but the theorem says that they are much different, even in terms of convergent sequences. Of course, weak star topology is never metrizable, but this is something else. Okay, and actually the theorem works for all infinite dimensional Banach spaces, but we are interested in this setting of spaces of continuous functions. So we have this theorem. So we had actually two motivations why we looked at this theorem. First of all, it's very useful. And second, it has an awful proof. Because all proofs actually go for this general case and are quite hard. Especially those one by Josefson Nissenzweig, those original ones are completely illegible. Then in 80s there was a proof which was a bit better by, I think, Hagler and Johnson. And in 96, Behrens found a very nice proof using some Ramsey theorem. So you can sit and read it. You don't need any knowledge to understand how he constructs general sequences of this form in Banach spaces. And when we wanted to move this situation to the spaces CK spaces, then actually it appeared that there are two cases of the proof. In fact, there is one case, because one is like that. If there exists mu n such that mu n weakly star goes to 0, and for every n the measures have norm 1, which is the conclusion of the theorem, and supports of measures are finite. I'm explaining what does it mean. Supports are finite. Then we are done. Of course, we are done in this place already, but let us assume that there is also such a sequence. So the other cases, no, there is no such a nice sequence which has all those supports finite. What is a support? Support is the biggest closed set, such that is the smallest closed set, such that when we look at the open set disjoint with this closed set, then the value of a measure is 0 on this set. So if we have our space K, then we have this nice set, this support, and whenever we take the open set here, then the value of a measure is 0 here. So this is the smallest such closed set. So here measure is always 0.
Is it always the smallest one?
Yes, in case of those nice regular finite Borel measures on a compact space, they always have a support. If the space is not compact, then just take the omega and take the ultra measure given by the ultra filter, non-principal ultra filter. It has no support. On each point, it's on each set. It's yeah.
And finite means actually a finite set.
And this is a very nice, just yes, the cardinality of support is just finite. So that actually means that mu n is of that form. Okay.
Sorry, can you?
Yes?
I'm confused as to why these exist. I mean, you can take the intersection of all the closed sets.
Yeah, I think so.
Measure,
Mm-hmm.
but the measure is just sigma additive. Why does the intersection have full measure?
Yeah, but you take closed sets, so what's the problem?
I mean, I understand if the space is second countable. I don't understand.
How it works in general case?
Yeah.
But
Am I just missing something stupid?
no, it's for every compact and those Radon measures, it always has a support, which is a closed set.
I'm just asking why. I mean, I get it.
Mhm.
It's second countable.
Yes, yes, yes.
But the issue is checking that the measures stay full.
Mm-hmm.
If you take this, it's the long decreasing sequence. At some point, the measure will be fixed on the set, and then so you can approximate it with counting many. You can take an intersection counting many of those sets, and you will get. Okay, what? What do you mean by this?
No, that's all the sets that you look at sets of measure 1, so there is no decrease anyway. But something could happen in an uncountable limit stage.
Okay, you mean that you drop the.
Maybe the intersection of omega 1 is null.
Okay, what I know is that and I saw this several years ago. It's in the Bogachev book. So, anyways, yeah. Okay. Can I? Okay. So we have this sentence in Bayer's proof, and then the other sentence is just so assume that we don't have such a sequence like that. Then he does some magic to obtain not such a sequence, but some other nice, maybe not nice, some sequence which satisfies the conclusion of the Josefson Nissenzweig theorem. So now the question is, maybe actually we are on this place, we are done. For all k, maybe always we have such a situation, and we don't have to go to the rest of the Bayer's proof, but we should prove that such sequence always exists. And so actually this was our first big motivation, and the other one was
You want to know if there exists one with finite supports.
exactly. Yes, this is our question: whether such sequences exist, whether the Bayer's proof can be finished here. And so it appeared that on the same time, Konkol, Banach, and Śliwa were working on the similar topic, and they came to the same sequences of measures, but it was connected with the problem of existence of separable quotients of spaces of continuous functions over Tikhonov spaces which are separable. What I said? Okay, so they wanted to answer the question if we take the space C of X, but with the pointwise topology, then does this space always have some subspace, linear topological subspace? If we divide by the subspace, that we get something which is separable. That was their question. And they proved something like that. So this is Banach, Konkol, and Śliwa, that X is Tikhonov, what we can think about compact. So they proved that Cp of K has this separable quotient, which is isomorphic to the space C0, and this is the space of all convergent sequences, all convergent sequences to 0 with the topology inherited from the just from the product topology.
Can you tell me what the second quotient is exactly? So,
okay, yes.
how do you form this?
Okay, so there was if and only if, but in a moment. So this is a linear space.
Yeah.
So we can, and it has the topology given by this pointwise. This is where here, yes, Rx. So it has the topology of this product topology. Mm-hmm. And now we look for some subspace of that, also a linear subspace, which is closed in this topology. Some say F subspace, such that whenever we take if we take the quotient, so this is the quotient like in linear algebra course, that we can divide the space by the subspace. And then we can put some topology on that, inherited from here. And the question is whether this is separable. So the question is whether we can find such F that it is a separable space.
Quotients, which is there's many quotients? No.
There can be, yeah, many different quotients, but it is important to find one which is separable.
Non-trivial.
You don't want them to space.
Yes.
So the only requirement on F is that it's proper linear subspace?
Closed.
Proper closed, though.
Yes. Closed is necessary to get that it's a Hausdorff.
But also infinite dimensional, because finite dimensional can get anything by Banach, I guess, something like that. It should be separate from infinite dimensional.
Yes, infinite dimensional. And they work on that problem because if we just use the topology, the norm topology, so we take the Cx, then it's already known that such a quotient exists. So they just wanted to get something stronger. Okay, and so they were thinking when actually we can find such a space F that this quotient is like C0. C0 is just the space of all sequences with domain, with the natural domain, which converge to 0, and they are real values. So they found that this the Cp of K has this separable quotient isomorphic to C0 with the topology from Rn, if and only if K admits a sequence like that. Like that. So this was.
Isomorphic means the bijection is both linear and a homomorphism.
Mm-hmm.
There's no metric.
There's no metric. This is not materializable usually. Yes, yes, yes. So the bijection is also, it's continuous with respect to this topologies, and this bijection is a linear isomorphism between vector spaces. Okay, so first one was just to understand. First motivation was to understand more this theorem. It's very useful. And the second one was that it came from the other side. And we know Banach and Konkel.
This property, does it mean somehow that K is somehow small or big? Or what?
You will see. You will see. So if we have this, so let us say that the space K has. When we were working on that, we called that actually the Josefson Nissenzweig property. But it's not a good name. It should be somehow mentioned that this is those supports are finite because for every K we have a sequence, but now we want to have special sequences. Anyway, let us call that has this Josefson Nissenzweig property if and only if there exists μn like that. So every norm is just 1. They converge on every function. They converge to 0, and the supports are finite. So actually, the measures are of this form. And very, very simple example is the following one. That K contains a convergent sequence, non-trivial. So all the elements are distinct. So when we look now on those point measures, they converge weakly star to 0.
Xn minus x?
Delta xn minus delta x.
Oh,
What's this 1/2 doing? What's that 1/2 doing?
So that
Yeah, the 1/2 is just that they sum to 1. When you look at the coefficients, they must be like here, they must, or like here, they must sum to 1. So, yeah, we need this 1/2. Actually, in many places, this is a bit redundant. It's necessary that the norms are always above some epsilon. Then you can normalize the measure that is divided by its norm, and this is the weak star convergence is preserved, and the measures get norms 1. Okay, so this has a norm 1, and it converges weakly star to 0. So yeah, when we have non-trivial convergent sequences, then we have those measures. This is simple, but actually it shows that many, I don't know, all metric spaces, all some Rosenthal spaces, all those spaces considered by topologies like, I don't know, Eberlein, Valdivia, Gulkon, and all they contains convergent sequences. So there we have those nice measures from the Josefson Nissenzweig theorem with this property that the supports are finite. Okay, so the counterexample, actually the counterexample comes from here, and counterexample is eta omega, and it was proved by them that it does not have the this nice sequence. So it a bit answers your question, but it's.
For example, I would expect a space which has a property that no convergent sequence.
Yes, so something in between.
Yes.
Okay, I will just come to this in a moment.
Beta omega is quite enormous, isn't it?
It is.
Like something small.
We need something small. But so let me show another example. Let A be a subalgebra of the power set of omega, such that the set A belongs to A, if and only if for almost all k, 2 to k belongs to A, if and only if 1 belongs to A. So this is the Boolean algebra containing all the sets, such that the even number is in the set, then the odd number must be, and vice versa. Okay, and this condition actually gives us that this is, when we look at the Stone space of this Boolean algebra, that this is a compactification of omega. And what is nice about this space, so this is the Stone space of A. First of all, it does not have any convergent sequence. No convergent sequences, no trivial. Second, it has lots of copies of beta omega.
A is not isomorphic to K omega?
It's not.
Oh, okay, not finite?
Because of
Okay.
And so 2, actually not because of 2, because of 3. It contains lots of copies, of beta omega.
So that's beta omega.
It has GNP. Namely, when you look at the sequence like that, 2 to n plus 1, it's weak star convergent to 0. So this space K has the GNP. Yeah, so you get something in between, in a sense. I think it's quite easy to see that it's weak star convergent, but okay, it's worth to mention that if we have a zero-dimensional space, then weak star convergent of measure is equivalent to be only weak star or to be convergent on characteristic functions on Clopens. So we don't have actually to check all the continuous functions. We need to only check those characteristic functions of Clopens. And this is with having this in mind, it's quite easy to prove that it's weak star convergent. Actually, it's immediate. Okay. Okay, so we have 2 examples. All of them are the same. When we talk about how the measure look like. So maybe this is always the case actually. If there is a GNP sequence, then it must be like that. So the answer is almost. There's say, a third example having GNP. It was invented by Banach, who proved that it has the GNP. It's in the same paper of Banach, Konko, and Shiva, but it was mentioned that it was due to Banach. And so we look at again at the Boolean algebra. Yeah, Banach is a master of measures on Boolean algebra. So every example he provides is always something with measures on Boolean algebra. Okay, so we take again this subalgebra of P of omega.
The same one, the one you wrote down there?
What?
It's the same one there.
No.
Oh, different.
That's gonna be a bit different example. So A belongs to A if and only if when we look at the density of the set, then it is either 0 or 1. Okay, and so this example has the property 1, it has the property 2, and it has the property 3, but in much more different form. So first of all, the stone space is again the compactification of natural numbers. And the measures look now like that. Recall that. We start with 1 over 2, but it's not all. Then we take by 1 plus 1. Sorry. Delta of I and delta of P, where P is an ultra filter of all those sets which have density 1. Yes, it's like that. Yeah, so density of is 1.
P contains this outer filter. Sorry.
It's a filter. Yeah, this is a filter in algebra.
And P is an outer filter extending it.
Mm-hmm. Yeah.
That's what equal.
No, this is not a filter.
In the Boolean algebra.
Oh, in this one, it's an outer filter.
Yes.
Yes.
So we have this. It's a point in the stone space. Yes. So.
Big elements of the algebra.
Yes. Okay. That works. This is a GNP sequence. So it works. And as we see, it has growing support. And actually, this Boolean algebra, or its stone space, has this property that there are no sequences, those nice G and Josefson Nissenzweig sequences with supports of some fixed size. If we have a Josefson Nissenzweig sequence which has finite support, then the supports must grow. This is the property of this Boolean algebra. So, yeah. But I say that we have almost the case like that because actually we have only two cases. If we have a sequence, if we have a Josefson Nissenzweig sequence with finite supports, such that the supports are the sizes of supports are bounded by some natural numbers, then we always can go to the supports of size 2. And on the other hand, we see that there are examples when this is impossible. In the same space. So actually, this is kind of dichotomy. Either we have sequences like that with growing supports, or we can go to to a sequence of measures which have supports like that.
You said in this case there are no bounded support sequences.
Yes.
J and P.
Mm-hmm. They are not. Mm-hmm.
So this is somewhat strong version and this very strong version.
Exactly. So maybe to write it. So compact is like that. So either okay, compact with GNP, of course. With the GNP. So then either there exists this MN UN such that supports size 2, or they go to infinity. Yep.
Or for all the sequences it goes to?
Hmm?
Do you mean or for all the UN such sequences?
Yes, yes, yes. Yeah. Okay. Good.
No, but I don't
It's
understand. This is not a proposition. This is just a case distinction somewhere.
yes, yes, yes. Then either there exists a sequence which has supports
Oh, I
like
see.
that.
Two is the point.
Yes, or for all GN with finite support, we have the situation like that. Okay?
Yeah, I see. So the point is that you can make it two. Finite is bounded is the same as two.
Yes. If we have bounded case, then we can always go to 2. Okay. Okay, so we have one characterization of those spaces which have those nice GM sequences. It's in terms of separable quotients of the space CPK. We can always also talk about characterize this property in terms of the space CK. So with the supremum norm topology. I need two notions. Okay, so first, let us say that K has the Grothendieck property. Grothendieck property. If and only if for every sequence of measures on K, not necessarily with finite supports, just a whole, such that they go to 0 in weak star topology. We have also the situation that for every Borel bounded function, the integrals go to 0, 2. So again, go to 0. So the Grothendieck property says that if we have a sequence of measures which goes to 0 on every continuous function, then it must go to 0 on every Borel bounded function. When we speak about K being zero-dimensional, this is the same as saying that if the sequence of measures goes on every Klopen set to 0, then it goes on every Borel set. Here we can, of course, since characteristic functions of Borel sets are Borel functions, this means that the measures go to 0 also on every Borel set.
So for stone spaces, is it the same as zero-dimensional, or follows from zero-dimensional?
Yes, if we talk about the stone spaces, then it's just, we can check here the convergence on Klopens, and this will imply the weak star convergence. This is because characteristic functions of Klopens form a linear dense subspace of the whole space CK. Yeah. Okay. So which spaces have the Grothendieck property? For example, all extremely disconnected spaces, extremely disconnected.
For Boolean algebras, this would mean complete Boolean algebras.
Mm-hmm. Actually, sigma completeness is enough. Yes, if we take the Boolean algebra, which is sigma complete, then its stone space will also have the Grothendieck property. Okay, so yeah, K is the stone of A sigma complete. And in fact, there are not too many other examples. This Grothendieck property is studied for many years, and it's completely not understood. It's very difficult, and the other examples which we have of spaces, compact spaces which have the Grothendieck property, are in fact somehow the modification of extreme disconnectedness. So the property is kind of still mysterious. But we have examples of algebras which are not sigma complete, but the spaces have the Grothendieck property. But when you look at the definition, this is not too far from being extremely disconnected. So anyway, there's a characterization in terms of the space CK also. It's very similar to this one by Banach and Konkel and Schliwa, and it was due to Schachermayer and I think Sembranos, and it says that K has the Grothendieck property, if and only if the space CK, I think, yeah, CK cannot be written as y plus C0, but now the C0 has a topology, norm topology given by the supremum norm. So Y is a closed space, closed infinite dimensional, closed infinite. C0, as I said, is the space of all sequences going to 0, but now we don't have the pointwise topology, but we have the topology given by the supremum of the values of the sequence. So it makes it as a Banach space. So if CK cannot be written as such a thing, So we cannot decompose it into two spaces, one of which is C0 and the other is some closed infinite dimensional space. Then the K has the Grothendieck property. So I think it's the same as having just the quotient, which is C0. So it's the same like Banach-Konkolschliwa theorem, but this speaks about Banach spaces, and this speaks just about topological vector spaces. So this is the difference. Okay, I will just for a moment we'll remove it, not to repeat the definition. But actually, this theorem suggests, and the theorem of Banach-Konkolschliwa suggests that there is some connection between the Grothendieck property and the GNP, and in fact there is. But we need something weaker, so we say that K has the, say, some M Grothendieck property. Condition is exactly the same, but now the measures are from the set mu, this mi, and mi is just a subset of Radon, of Radon measures. So for every mu n, weakling star going to 0, now they belong to mu. We have that for every Borel bounded go to 0. So this is exactly the Grothendieck property, but we just restrict a bit the area from which we take measures. And so in this mu k, we can distinguish two spaces, which are nice. One is denoted by L1 on K, and this is just the space of all measures which have countable supports. So they are like, I remove it. So they are just this, when you can write them as the countable sum of Dirac's deltas, and that's it. So we belong here if the support of mu is countable, and the other space is just the linear span of this embedding of K. So this is just the measures as we work now with. These are just the measures with finite supports. So support of me is finite. Okay, so those are the most important me's for us. And now the proposition is as follows. For every space K, the following are equivalent. First of all, K does not have the L1 Grothendieck property. Second, K does not have this span of delta of K Grothendieck property. So this is equivalent. Third, K has the GNP. And fourth, K has the GNP, but now we can talk about the measures which have countable supports. So there exists a sequence mu n in N1 case such that mu n goes with star 0, and mu n has have norm 1. Okay, so actually it appears that this GNP property is equivalent to the weak form of the Grothendieck property. So now the question is whether we can write here the 0.5 or say 0 and say K does have the Grothendieck property. Maybe those are equivalent. And it appears that it is not the case. We have another example by Banach, which is unpublished. So this is, say, again Banach. There exists a space K. It's again a stone space of some Boolean algebra, such that it has two properties. K does not have the Grothendieck property, not have the Grothendieck property, but every separable subset of K has the Grothendieck property. And the second condition implies that it has the L1 Grothendieck property. Yes, because if it has the GNP, then just take the sequence GNP, take the closure of union of supports, then it's a separable set. Then it says, our proposition says it does not have the L1 Grothendieck property, but we know that it must have the Grothendieck property, so it's a contradiction. So okay, so we have the example which distinguish those two cases. So now the question can be, can we have the K be separable? So K is separable, and it does not have the Grothendieck property, but it has the L1 Grothendieck property. And yes, we can construct such an example. Okay, so let K be extremely disconnected. Disconnected. Then there exists the space L, and there exists a continuous surjection from K onto L. Such that L has the L1 Grothendieck property, but not but not the Grothendieck property. So when you look at by the Stern duality, when you look at the Boolean algebras, then we can say that every complete or sigma complete Boolean algebra has a subalgebra which stone space has this L1 property, but the space does not have the Grothendieck property. Of course, if we don't take the countable subalgebra, then it does not have even the L1 Grothendieck property because the stone space is metric space. So it has convergent sequences. Okay. Okay, I can actually show how is it more or less constructed. So sketch of the proof. We start with this K, which is extremely disconnected, infinite. So we can find on it a probability measure. Probability non-atomic measure. Probability means that it's a positive measure and has norm 1. And now we take the entire chain of Clopens. So entire chain of Clopens. Okay, entire chain means that they are pairwise disjoint, such that the measure is positive on each an. And now we find a special set. It's a closed set. It's non-empty. It's a set of such points.
Maximal antichain?
No, just countable antichain. It's such a set that whenever you look at its Clopen neighborhood, Clopen, then the measures, the measure mu on the intersection of this Clopen with this entire chain is big with respect to the entire chain. So it's positive. Okay, this is non-empty. This is a closed set. It sits somewhere in the boundary of the union of the entire chain. So when you have this entire chain, ions, so it must be somewhere here, but it's not the full boundary, probably. So these are ions, and this is the set F. Okay, and what you do now is just take the quotient of K modulo this set F. And this is this space L.
Quotient means you identify the points?
Yes, yes. F is just going to one point and the other points are just stay. Okay, and this is this L and it has this properties.
Translate it to Boolean algebras, please. Should be trivial.
It's just a subalgebra. It's the stone space of that thing is no, the algebra of Clopens is just the subalgebra of K of this sigma complete Boolean algebra. It's a subalgebra.
So F is what? F is a
So everything which either completely contains F or is disjoint from F. Take all closed sets which is completely
yes.
contain F completely or disjoint from F. That's the name is subalgebra.
And F is a space. F are the points. There's an object.
Mm-hmm.
Okay.
Okay. So just the argument why it does not have the grothending property. So we have to define some measures which go on every clopen to 0, but not on every Borel set. So we need the projection. The projection is projection goes from here to F, and A is clopen. So this is just mu of A. Wait. Okay, yeah. AN pre-image of A by C. So it's quite easy to see that this goes to the weakly start to the point, the singleton of this point F. Do you see it, more or less? Just check it on clopens, it's enough. So a clopen. If it's disjoint, the clopen is disjoint with this point, does not contain this point, then it means that it's disjoint with F when you project it back. So this must be 0. That's what we wanted. So it does not contain the point, so delta is 0. If it contains, then look at its complement, and it has the complement on the complement it has the value 0. So just so it just means that on this set must be the measure 1. It's getting hotter and hotter. Yes, is it? Okay. Proving that it has the L1 grothending property is much more difficult, so I will skip it. Okay. Oh, by the way, this is the modification of this example of this example, actually. Banach. Okay, so and before we had this example, we are thinking on something else, how to get such an example, but separable. So separable space, which does not have the grothending property, but has the L1 grothending property. So there is a theorem of Sembranos and Fenisha. Sembranos and Fenisha, I think it's 84, that for every two compact spaces K and L, infinite, The product has the grothendieck property. What? It does not have. Yeah. Does not have the grothendieck property, and the proofs are not easy. They need lots of theorems, functional analysis, and what they use in the first step is just taking some sequences of measures from the Josefson Nissenzweig theorem, and then they do something with this. So it again shows that it has something in common and that this theorem is powerful. Okay, so even if we take here two extremely disconnected spaces, then the product will not have the grothendieck property. So the product is a very nice thing. It kills the grothendieck property. Okay, so as I said, we wanted to get the example which does not have the grothendieck property but has the L1 grothendieck property. So we thought, okay, so maybe it does not have the grothendieck property, but maybe it still has the L1 grothendieck property. So we started to prove it and to construct, to prove that, for example, beta omega times beta omega has the grothendieck property, has the L1 grothendieck property, and we had like 2 or 3 proofs, which were all, of course, bad. And then I asked at math overflow, because what we wanted to do was, it was something like that. Okay, we have this beta omega. We have another beta omega here, so we have a product. Okay, so assume we have this GNP sequence. So it has some supports. Those supports, when we look at the projection, they can be very interfering each other. So they can be like that, actually. And we wanted, okay, so what we wanted to get is, assume that this product has the GNP property, then let's somehow project it to the beta omega and get the contradiction. Because we know that in beta omega there is no such a sequence. Okay, so because it can be very in this form that when we project, actually we can get that we can define the measures because everything will cancel each other. Those coefficients will sum to 0. So we thought, okay, so maybe let's do something like rotation of beta omega, whatever that means. And just to move it, like shake it so nothing will project to the same values. And actually this question is about getting non-trivial functions from the product of beta omega times beta omega onto the beta omega. And so we found like 2 such functions. We thought that they are continuous, but in the end they appear to be only Borel, which is not good. So I asked on the math overflow, and KP Hart answered me that there are no such mappings, because if we have this beta omega, then due to the result of Elias-Farah, we can always divide it into rectangles, finite cover by rectangles, somehow like that, such that this map on each rectangle will depend only on one coordinate. So in fact, it will be trivial. It will be just the normal projection, so we cannot get any non-trivial mapping. This is the result. ZFC. And it works for any kappa, any, I think, regular cardinal. So this is by Elias Farah. Okay, so it showed that this kind of way of proof cannot work. So we said, okay, so maybe they exist, those Josefson Nissenzweig nice sequences. So we started to construct them just by hand, writing, and after several definitions, we got that they may exist, but they must be very, very complicated. And then we looked into the book of Bolobas on random graphs and so on. And we started to learn random graphs and probability, and we constructed it, and it appeared actually not that hard. So I will just make a picture how to get it. We need only omega times omega, actually. So we construct the GNP sequence in the product beta omega times beta omega. So we divide omega times omega into the squares. Say the first square has size, okay, let it be first one. So it will be has the size, I think, right, 2 to 0. Okay, the first one has like just 1 times 1. The second one is bigger. It has 2 values, so 2 to 8 down, it's a 4. Okay, so it's like that. So it's 2, 4, and bigger. So here we have the size n, and here we have size to, I don't remember, I think 2 to n. Yes, I 2 to n. Such squares, and then what we do inside, each such square will be a support of one measure, of the nth measure, and it will be defined like that. Just look on that thing. So we have 2 to n sequences, and just put pluses and minuses in such a way that every sequence occurs somewhere here, and normalize it by n to 2n. Don't care how is it distributed, just put all such sequences here and normalize it. And so in each point it has, let's say, like -1 n to 2n, or there is some 1 n to 2n, and just be sure that everything is distributed in this way. So the measures are just defined like that. So these are over those sigmas, -1 to 2n, 1, yeah. Sorry. N to 2n times n and here's some coordinates. So the measures are just those rectangles here, and so they have. It's easy to see that they have norm 1. It's a bit harder to see that they converge to 0 on every clopen, because we need to use something like law of large numbers, something like that. And what's the idea? We need to look to prove that it is Weak-star converges. We need to look only on clopens. Clopens are compact, so in fact we need to look only on basic clopens. So we have this support of a measure, and we have some set x in omega, some set y in omega. So we look at those intersections of points. And what is the idea? The idea is that if we go to n, then the values of measures must go to 0. Why? Because, well, what are the situations here of intersection? If it hits many pluses and hits many minuses, then it's very close to 0. If it hits many pluses but not too many minuses, then it does not go to 0, but such situation, because of those theorems from probability, occur very rarely. And actually, the places when there are only many pluses or many minuses are very rare. So in total, when we sum this thing up, it will be smaller than sum 1 over n, and in fact, it will go to 0. So the idea is just to consider two cases. Either everything cancels, or if it's not cancelled, then it's very, very, say, boundary case, and having no impact on the general convergence. Okay. So this is that. Now, if we have such a sequence in beta omega times beta omega, then we can get, in fact, in any k times L. It's not only necessary to say take one discrete set D in 1k countable, E in L, and now we have by the Stone duality, by the Stone extension property, we have a mapping onto the product of those closures. It sits inside k times L, and we can, because this is the measures were defined on disjoint supports, and on omega we can transform the measures just directly onto D times E. So we get the measures will be completely unchanged. They just move perfectly onto D times E, which sits in k times L, and the all convergence and norms will be preserved. So, in fact, in product we get those Josefson Nissenzweig nice sequences. So it proves that k times L does not have the Grothendieck property, and in fact it does not have the L1 Grothendieck property. And I think I will end now.
Curious about one thing. I mean, Grothendieck is known for so many things. What was he? Why is this called the Grothendieck property?
Because he was the first one who studied it, yes, but it was in 55 or 56, and just after that he skipped immediately to those algebraic geometry.
Oh, you mean there was a field shift? I see.
Exactly, yes.
Analysis, and then he started doing algebra.
Yes, I think it was one of his last works in functional analysis. He was still in Brazil, and then he...
Oh, he was under Brazilian influence.
Yeah. I think he said something that there is nothing more to be invented in the topological vector spaces. So, yeah.
Like Cohen saying there's nothing more to do in set theory?
What is the situation with the original question when you have when you only this finite support? So is it equivalent?
So because it's now it speaks about Grothendieck properties, it shows that it's not easy to find the characterization. But besides of that, we, for example, have also that say all nice Efimov spaces, so those spaces which do not have copies of beta omega nor copies of converging sequences, they do have the GNP. I mean that they are constructed by minimal extensions, the limits of inverse limits of some special systems, and most of them which we know today are constructed in such a way. So by piece, we know some pieces in which have the GNP and which do not have the GNP for sure.
But it could be the case that whenever you have this weak GNP, then you insert it.
No, because we have this Grothendieck property that exists, yes? And so beta omega does not have this finite supports in GNP sequences, cannot have.
Yes.
Actually, you can also prove that if K has this Grothendieck property and you have the GNP sequence, the sequence from original Josefson Nissenzweig theorem, then when you look at the part of the sequence which is atomic, then this part is completely negligible. It goes to zeros in norms. So you can just restrict your measure to something which is not atomic. So Grothendieck property is completely killing the case. And so to understand it good, we need to understand the Grothendieck property. And as I said, mankind is far from it.
So here you're a functional analyst, not a set theorist.
Yeah, it's more about topology, general topology.
I didn't, the word forcing was not mentioned today.
It wasn't.
That's surprising.
I'm surprised, yes.
Well, there is a nice question which says, take the label force, just add one label here, and take a favorite, completely countable closed Boolean algebra in the ground level. Will it stay perpendicular in the forcing extension? If the answer is positive, you get the alternative of some completely ununderstood as a result of Talleyrand, which is not understood not only because it is in French, but
Yeah.
for many other reasons.
Other comments? Thank you again.
Thanks.